Welcome, curious minds, to the deep dive. Today, we're plunging into a critical global challenge, one that impacts millions of lives every single year: urban air pollution,
It's a huge one. You see the headlines, you sometimes feel it yourself.
especially in those mega cities, right? Like Delhi. We're talking
Yeah.
about something the World Health Organization links to, well, literally millions of premature deaths annually.
It's staggering, and it's not just an environmental talking point, it's a profound public health crisis.
Exactly.
Yeah.
And it demands innovative, smart solutions, which brings us to our topic today.
The conventional approaches, regulations, green spaces, they help, but they often struggle.
They struggle to keep pace, especially with how dynamic cities are.
Precisely. The pollution changes hour by hour, street by street.
And that's exactly where our deep dive begins. Our mission today is to unpack a really groundbreaking research paper. It tackles this exact problem using cutting-edge artificial intelligence.
Yeah, this is fascinating stuff. We're looking at deep reinforcement learning.
Specifically, an algorithm called Proximal Policy Optimization, or PPO. We're going to explore how it can be used to strategically place air purification booths in these big metropolitan environments. And we'll be focusing, as always, on the technical details and implications.
It's like teaching an AI to become a super smart urban planner, but specifically for air quality.
Optimizing where to put these booths in a way traditional methods just can't.
Right, learning from the environment itself to make these really precise decisions.
Yeah, so by the end of this deep dive, you'll have a clear understanding of how this flavor of AI, this DRL, can be used for spatial optimization in smart cities.
And you'll get some surprising insights into the technical nuts and bolts that let these algorithms make such informed decisions.
Decisions for public good, which is the exciting part here. This isn't just theory. It's a practical application of advanced AI tackling a massive environmental and health issue.
Consider it your shortcut, maybe, to being really well informed on this intersection of AI and environmental management.
Okay, let's unpack this. So let's start by framing the sheer scale of the problem. Air pollution truly is a global crisis, isn't it?
Absolutely. We're not just talking about hazy skies or a bit of smog.
And no, we're talking severe health consequences,
Hmm.
respiratory conditions, cardiovascular problems.
And even reduced life expectancy across the board. The health burden is just immense, and it's really well documented.
PM 2.5, PM 10, all those particulates we hear about.
Exactly. Long-term exposure to those, plus things like nitrogen and sulfur oxides, it has clear links to chronic diseases, higher mortality rates.
Especially hitting vulnerable groups hard, like kids, the elderly.
That's right. And the economic costs are staggering too.
Yeah.
Increased healthcare spending, lost productivity from people being sick, just a lower quality of life overall.
And Delhi, as you mentioned, it's such a stark example of this crisis playing out.
Yeah, unfortunately, it consistently ranks among the most polluted cities globally. Those PM 2.5 and PM 10 levels, they're often way, way beyond what's considered safe.
It's just this incredibly dense, active city. Almost a perfect storm for pollution challenges.
Delhi's situation is really acute. The sources are complex. You've got pervasive vehicle emissions. The number of cars is just exploding. Then there's extensive industrial activity, constant construction kicking up dust.
Right.
And then the big one, seasonally, is the crop burning from nearby states. That just exacerbates everything.
Especially in winter, I gather.
Exactly. You get these temperature inversions, they trap the pollutants near the ground, and the concentrations just spike dramatically. It's pretty bad.
Okay, so given this monumental challenge, why haven't the traditional methods really solved it? We hear about emission regulations, green infrastructure. Are they not working?
Well, they are effective in principle. They're definitely vital long-term strategies, but they have these inherent drawbacks that make them slow to adapt.
Slow, how so?
Well, emission regulations, for example, they need sustained policy enforcement. That often runs into, logistical hurdles, political roadblocks. It takes time. And green infrastructure, planting trees, creating parks, that's great, obviously. But it's a slow, often costly process. It doesn't give you immediate targeted relief for those acute pollution hotspots.
So good foundational steps, but not a quick fix for these rapidly changing urban pollution patterns.
Exactly. They're not agile enough for the day-to-day reality.
What about more localized solutions, like those air purification booths you sometimes see? They seem like a more immediate approach.
They do, and the idea is sound. The problem is their actual impact is often pretty suboptimal.
Why is that?
It usually comes down to simplistic, static placement strategies. They just put them somewhere and leave them.
Like maybe where the pollution was worse last week.
Kinda, yeah. Think about it. If you place a booth based on a single past measurement, it's like shooting at a moving target with your eyes closed almost.
Right. You might get lucky sometimes, but you're definitely not optimizing for the complex, shifting reality of the city's air.
Precisely. Which brings us to what the paper calls naive placement versus dynamic factors.
Okay, break that down. What's naive placement?
Naive placement refers to those simpler existing heuristic or rule-based methods. Like the most obvious one. Just stick the booths in the zones with the absolute highest air quality index or AQI readings.
Seems logical on the surface.
It does, but it fails to account for the dynamic, multifaceted nature of the city. It ignores crucial things.
Or what?
Like fluctuating traffic patterns. Pollution sources can shift dramatically depending on rush hour or even just the day of the week. Or varying industrial influences. Maybe one factory has a huge impact, but only in a very small area or only at certain times. Simple rules miss that nuance.
And then there's the whole people aspect. It's not just about where the pollution is, but where the people are being exposed to it.
Exactly. That's a huge point.
Yeah.
A static, high AQI approach might clean the air in, say, an unpopulated industrial zone.
While leaving a densely packed residential area, maybe with slightly lower AQI but way more people, completely unaddressed.
Precisely. So you end up with this uneven AQI distribution, and you're not really achieving the most effective long-term improvement for the population.
The complexity is just immense.
It really is. Finding the optimal booth placement, it requires this delicate balancing act. You need to weigh population density, traffic congestion, industrial emissions, ensure decent spatial coverage without wasting booths.
It's a massive, multivariable optimization problem.
In a constantly changing environment, no less.
So traditional methods just hit a wall. They can't handle that level of complexity and dynamism.
Pretty much. They're too static, too simple.
Okay, so here's where the AI comes in. This is the breakthrough part. Deep reinforcement learning for strategic urban intervention. How does DRL specifically overcome these limitations?
Right. So deep reinforcement learning, DRL, it's a powerful approach. It's data-driven, and it's uniquely suited for these complex sequential decision-making problems, like pollution control, like urban planning.
How does it work differently?
Unlike those static models, DOL agents learn the best policy, the best strategy through trial and error. They interact with a simulation of the environment.
So they try placing a booth, see what happens, get a reward or penalty?
Essentially, yes. They learn from feedback. And crucially, they dynamically adapt to uncertain and changing conditions. They don't just calculate one single best spot based on past data. They learn a strategy for how to choose spots over time, constantly refining that approach based on new information.
That sounds much more suited to a dynamic city. And the algorithm they used here is Proximal Policy Optimization, PPO. Why PPO? What makes it special for this?
PPO has become sort of a go-to algorithm in DRL recently. It's known for being robust and pretty effective, especially when you have these high-dimensional, complex action spaces, like choosing from thousands of possible booth locations.
Okay, robust how? What's the core innovation?
Its main innovation is something called the clipped surrogate objective.
Clip surrogate objective. Okay, what does that mean in plain English?
Yeah. Think of it like putting guardrails on the AI's learning process. This mechanism, this clipping, it constrains how much the AI's policy can change in a single update step.
So it stops it from making massive, sudden shifts in strategy, like going from placing booths only in the west 1 minute to only in the east the next.
Exactly. It prevents overly large, potentially destabilizing changes during training. It forces more gradual, controlled improvements.
Which sounds important when you're balancing so many factors.
Absolutely critical. In a complex problem like this juggling AQI, population, traffic industry, you need that stability. Without clipping, one large update could accidentally mess up a good strategy the AI had already learned. PPO helps maintain that balance.
So it learns more steadily. Does it also help with exploring new options versus sticking with what works?
Yes, it manages that balance really well too, the exploration versus exploitation trade-off. It needs to explore, try new placements to see if they're better, but also exploit the strategies it already knows are effective. PPO handles this efficiently, which is key in these challenging environments where the best solution isn't obvious up front.
Makes sense. So using this PPO algorithm, what were the main goals of this research? What were they trying to achieve and contribute?
They laid out several clear objectives. First, Obviously, develop this RL-based strategy for optimal booth placement.
Okay.
Second, compare how well it performs against those traditional methods, the random placement, and that simpler, greedy strategy of just targeting the highest AQI spots.
Right, the benchmarks.
Exactly. Third, evaluate performance using a whole suite of metrics. Not just did the average AQI go down, but also things like impact on population centers, impact near heavy traffic, how well it covered the area spatially, and even a measure of spatial balance or entropy.
So much more holistic view of good.
Very much so. And finally, their goal was to highlight both the benefits and, importantly, the limitations of using this kind of AI optimization for real-world air quality management.
What strikes me as really novel here is that emphasis on continuous learning and adaptation. Unlike just picking spots once, this DRL approach keeps learning as conditions change, right?
That's the key differentiator. Static placement is a one-shot deal. The DRL approach continuously learns and adapts. If traffic patterns shift or a new industrial zone pops up, the AI can, in principle, adjust its strategy over time.
That feels like a huge leap for urban planning tools.
It really is. It makes the solution potentially scalable and adaptable to different cities, not just locked into Delhi-specific initial conditions. And that multidimensional evaluation framework is also vital.
The one considering population and traffic impacts.
Yes. It forces the placement strategy to think beyond just raw AQI numbers. It has to consider the social and logistical factors. Where do people live? Where do they move? What about industrial impact? It ensures a more holistic, arguably more equitable outcome.
Moving beyond just technical optimization to thinking about community benefit.
Exactly. That's a really important aspect of this work.
All right, let's pull back the curtain then. Let's get into the nuts and bolts of how they actually built this intelligent system. The methodology deep dive, the paper describes it almost like a data pipeline, right? From raw data to the final optimized placements.
That's a good way to think about it, yeah. Like a funnel. It starts broad with data collection and cleaning, gathering all the necessary air quality data, traffic data, population data, etc., and cleaning up inconsistencies, missing values, garbage in, garbage out, right?
Standard data science practice.
Absolutely. Then comes pre-processing. This is where they standardize the data, maybe scale it, fill in any remaining gaps using smart techniques, get it ready for the AI.
Okay.
After that is environment modeling. This is crucial. They create a detailed, multi-layered digital twin, essentially, of the city. A grid representing Delhi with all these different factors overlaid. This is the world the AI agent operates in.
The simulation space.
Precisely. And finally, the reinforcement learning stage itself. This is where the PPO agent gets trained within that simulated environment, learning through trial and error to make the optimal placement decisions based on all that detailed environmental data.
So it's a systematic pipeline. Data collection, cleaning, pre-processing, modeling the environment, and then the RL training.
Exactly. Each step builds on the last, ensuring a high-fidelity representation of the city gets fed into the AI for learning.
Let's dig into that first stage, data collection and pre-processing. The paper makes a point about the limitations of relying only on a few official monitoring stations. Why isn't that enough for a city like Delhi?
It's a really critical point. Urban environments are incredibly varied, spatially heterogeneous. A handful of monitoring stations, even if they're accurate, are just too sparse.
They miss things.
They miss a lot. They miss local variations, microclimates caused by buildings or parks, crucial contextual details. You might have a station showing decent AQI overall for a neighborhood, but miss a massive pollution hotspot right next to a busy intersection or a small factory just a few blocks away.
You need finer-grained information for targeted action.
Exactly. To make truly effective localized interventions, like placing these booths, you need a much richer, denser understanding of the pollution landscape.
So their solution was an integrated data strategy. What different data sources did they actually combine, and why was that fusion so important?
They pulled together several key types of data. First, the obvious one. Station-based AQI data.
Yeah.
Hourly measurements from the existing physical sensors scattered around Delhi. That gives you the ground truth, the baseline.
Okay, official readings.
Right. But to fill the gaps between those stations, they incorporated high-resolution AQI estimates from a commercial API. This provides a much denser spatial picture.
An external data source, did they just trust it?
No, crucially, they cross-validated it against the station data. They checked if the API estimates lined up reasonably well with the ground truth readings where they overlapped. That's important for ensuring data quality.
Good practice. What else?
Third, they brought in custom data sets. This involved geospatial data from sources like OpenStreetMap and the Delhi Development Authority,
What kind of information did that provide?
really detailed city-scale insights, things like the precise locations and sizes of green spaces, water bodies, industrial zones, also detailed population density maps, and data on traffic hotspots, major roads, intersections, flyovers.
Wow, okay. So a really rich mix.
Yeah, and the fusion of all these sources is what makes it powerful. It allows the model to capture both the large-scale pollution trends from the stations and API and those vital local variations and contexts from the custom datasets. It ensures the AI isn't operating blind, but has a comprehensive picture of the city.
Got it. So once they had all this raw, diverse data, how did they process it? What did the pre-processing pipeline involve?
There were a few key steps. First, handling missing data. For any missing AQI measurements from the stations, they used median imputation,
Meaning?
meaning they estimated the missing value by taking the median AQI from the nearest neighboring stations at that time. It's a reasonable way to fill gaps using spatially relevant information.
Okay.
Second, normalization. This is standard machine learning stuff. They rescaled all the different features, AQI, population density, traffic counts to a consistent range, usually between 0 and 1.
Why do that?
It prevents features with naturally large numerical values, like maybe raw population counts, from unfairly dominating the learning process compared to features with smaller ranges, like a scaled AQI value. It ensures all features can contribute meaningfully to the AI's decision-making without scale bias.
Right.
Makes the training more stable.
Right. Levels the playing field for the features. Then what?
Then comes spatial interpolation. This was key for creating that uniform grid the AI needs. The point measurements from the AQI stations had to be converted onto a dense 50 by 50 grid covering Delhi.
How did they spread the station data across the grid?
They used a technique called inverse distance weighting, or IDW. Basically, for each grid cell, the AQI value is calculated as a weighted average of the nearby station readings. The weight given to each station decreases the farther away it is.
The closer stations have much more influence on a grid cell's value.
Exactly. It makes intuitive sense and reflects localized conditions well. They use a specific parameter, P2, which is common in IDW, for a smooth decay of influence.
Okay, so now they have a grid of interpolated station AQI. What about the API data? How was that fused in?
Good question. For the final data fusion step, they combined the interpolated station-based AQI grid with the high-resolution API estimate grid. For each grid cell, they simply took the maximum value between the two sources.
The maximum. Why?
It's a conservative strategy. By taking the maximum, they ensure that they don't accidentally underestimate the pollution in any given area. It prioritizes identifying the potential worst-case scenario in each cell, making sure no critical hotspots are overlooked when deciding where booths might be needed most.
Got it. A safety-first approach to mapping the pollution.
Precisely.
Okay, so that covers data collection and prep. Let's move to environment modeling, capturing that urban complexity. They chose a 50 by 50 grid for Delhi. Why that size? What's the trade-off?
50 by 50 grid choice is all about balancing granularity versus computational feasibility. Each cell ends up being roughly 1.2 kilometers by 1 kilometer in Delhi.
Is that detailed enough?
It's considered a reasonable resolution for this kind of problem. It's fine enough to capture significant spatial variations in pollution and the typical influence radius of these purification booths, but crucially, it keeps the total number of grid cells manageable.
What if they used a much finer grid, say 100 by 100?
A finer grid would give more detail, yes, but it would drastically increase the size of the state space the AI has to learn about. That means significantly more computational power needed, much longer training times. It could become prohibitively expensive or slow. So 50 by 50 was a pragmatic trade-off.
Okay, and within this grid, they used that multi-channel representation, like different layers on a digital map. 6 distinct channels, you said.
That's right. This multi-channel approach is key to giving the AI a rich understanding of the state of each grid cell.
So what are the 6 channels? What does each one represent?
Okay, first, the AQI grid. This is that 50 by 50 layer showing the baseline air quality derived from the fused station and API data we just discussed. It's the core pollution map.
Got it. Number 1, AQI.
Second, the population grid. This channel represents population density across the city. Cells with higher population density get higher values, indicating areas where more people are potentially exposed.
Makes sense. Third.
Third, the traffic grid. This reflects traffic density. It's typically derived from data about major intersections, flyovers, maybe daily vehicle counts on main roads. Higher traffic areas get higher values.
Okay, AQI, population, traffic. What's next?
Fourth, the industrial grid. This represents the influence of known industrial zones. The value in a cell might depend on the size of the nearby industrial area, maybe the type of industry. These often have strong, localized pollution impacts.
So those four seem to represent sources of pollution or areas of high exposure. What about the other two channels?
Right. The fifth channel is the green space grid. This layer maps out parks, forests, water bodies, the natural elements. Importantly, the way this channel is used is often to discourage booth placement.
How so?
Areas with a high value in the green space grid might be excluded as potential booth locations, or the reward for placing a booth there might be penalized. The idea is to preserve these natural areas and their own benefits.
Clever. And the last channel.
The sixth is the booth grid. This one is dynamic. It simply keeps track of where booths have already been placed during the simulation or planning process. When the AI decides to place a booth in a cell, that cell gets marked in this channel.
So the AI knows where booths already are and avoids putting too many close together.
Exactly. So each grid cell isn't just a single number. It's a vector containing values from all 6 of these channels. This gives the DRL agent a really comprehensive snapshot of the environmental state at that location.
That's a very detailed representation. Let's dig a bit deeper into how they modeled the influence of these features: population, traffic, industry. You mentioned Gaussian kernels and radial decay. What's the thinking there?
The core idea is realism. The influence of something like a busy highway or a large residential block doesn't just stop abruptly at its boundary. Its effect, whether it's pollution generation or population exposure, spreads outwards and typically decays with distance.
Okay, the impact fades the further away you get.
Precisely. They use Gaussian kernels to model this smooth decay mathematically. So the influence value of a feature like traffic at any given grid cell depends on how far that cell is from the source of the influence, the highway. The further away, the lower the calculated influence.
And within that Gaussian model, they have parameters like weight and spread. What do those control?
These parameters are crucial for tailoring the influence model to different types of features. The weight, W, basically determines the maximum strength or importance of the influence at its source. The spread, sigma, controls how quickly that influence decays with distance. A larger sigma means the influence spreads out further.
Can you give some examples? How might the weight and spread differ for, say, traffic versus green spaces?
Sure. For traffic density, you'd likely assign a relatively high weight because traffic is a major pollution source, but maybe a smaller spread, like a sigma of maybe 200, 300 meters. Traffic pollution tends to be quite concentrated near the roads.
Okay, strong but localized.
Right. For population density, the weight would also be high, representing exposure risk, and the spread might be larger, say 500 meters, reflecting how people move around a residential area.
Wider influence.
For industrial areas, the weight could be very high, but the spread might be quite small, maybe 100, 200 meters, if it's a point source like a smokestack. And for green spaces, the weight in terms of attracting a booth might be low or negative, but the spread could be large, maybe 700 meters, reflecting the broader area benefiting from the green space.
So they tune these sigma values based on the expected real-world behavior of each feature.
Exactly. It's about capturing the spatial dynamics realistically. They also use a radial influence function, often a linear decay based on distance, to translate these Gaussian parameters into specific influence values for each grid cell. The total influence on a cell is then the sum of influences from all nearby features.
This detailed influence modeling gives the AI a much more nuanced understanding of the urban landscape to work with.
Absolutely. It moves beyond simple proximity to capturing graded, overlapping zones of influence, which is much closer to reality.
Okay, now let's talk about the booths themselves, the placement dynamics and constraints. How did they model the effect of placing a booth? Does it just magically clean the air in its cell?
No, it's more sophisticated than that. They model the booth's impact on the surrounding AQI also using a Gaussian decay function, similar to the feature influence, but this time modeling the reduction in AQI.
So the cleaning effect is strongest right next to the booth and fades outwards.
Precisely. The function has parameters defining the maximum AQI reduction possible right at the booth location. They call this IA, alpha, and set it based on empirical data, maybe 60% reduction, and a spread parameter, sbooth, sigma booth, defining how far that cleaning effect reaches effectively.
Okay, that sounds realistic. Now, the reward function, This is the heart of the RL process, right? How the AI learns what a good placement actually is.
Yes, this is absolutely critical. The reward function guides the entire optimization. It's the signal telling the AI, you did a good job or that wasn't helpful. Because there are multiple goals, they used a multi-objective reward function.
Meaning it gets rewarded for achieving several things at once.
Exactly. The total reward for placing a booth wasn't just based on one thing. It was a weighted sum of several components.
Like what?
Like our local, the immediate AQI improvement right where the booth was placed. Then our global, the overall improvement across the whole city grid, encouraging broader impact.
Okay, local and global AQI.
Then, crucially, our population, our traffic, and industrial. These components weighted the AQI improvement based on the population density, traffic levels, or industrial influence in the area affected by the booth.
So reducing AQI by the same amount gives a bigger reward if it happens in a densely populated area or near heavy traffic.
Precisely. This explicitly guides the AI to prioritize placements that benefit more people or tackle major pollution sources. It directly incorporates those social and logistical factors into the learning objective.
That's clever. Is there anything else in the reward function?
Yes, there's also usually a penalty term, P. This subtracts from the reward if the placement violates any of the predefined constraints.
Like placing a booth too close to another one.
Exactly. Or placing it in a green space or an area with very low population. The weights for all these reward components, our local, our global, our population, etc., and the penalty term are carefully honed through experimentation to achieve the desired balance between objectives.
It's a complex balancing act, just designing the reward signal itself.
It really is. Designing a good reward function is often one of the hardest parts of applied reinforcement learning.
And speaking of constraints, what specific rules did they implement to make sure the AI suggestions were actually feasible in the real world?
This is super important for bridging the gap between simulation and reality. They implemented several key constraints, often checked by a function like valid cell XY.
What were they?
First, minimum interbooth distance. They use the Haversine formula to calculate the real-world distance between potential placements, and ensured booths weren't placed too close together, maybe needing to be at least a kilometer apart to avoid redundancy and wasted resources.
Okay, spacing them out.
Second, a population density threshold. Booths might only be considered for placement in cells, where the population density value exceeds a certain minimum level, ensuring they're actually serving populated areas.
Makes sense. Don't put them in empty fields.
Right. Third, an AQI improvement potential constraint. A placement might only be valid if the model predicts it will reduce the local AQI by at least a certain amount, say 10 AQI units, ensuring each booth makes a meaningful contribution.
So no placements with negligible impact.
Exactly. Fourth, green space exclusion. As we discussed, cells with a high green space value, say above 0.5 on their normalized scale, were deemed invalid placement locations. Got to preserve those parks. And finally, a maximum booths constraint. There's always a budget, right? The total number of booths the AI could place was limited, reflecting resource constraints.
These constraints seem vital for making the AI's output practical and actionable.
Absolutely. Without them, the AI might suggest theoretically optimal but completely unrealistic placements.
Okay, this framework sounds incredibly robust. Let's dive into the PPO algorithm itself now. We touched on why it's good stability, sample efficiency. Can you elaborate on why those are so crucial here?
Sure. Stability is paramount because urban environments are complex, noisy. You don't want your learning algorithm to suddenly diverge or collapse because of some unexpected data fluctuation. PPO's clipping mechanism provides that crucial stability.
Keeps it learning steadily.
Right. Sample efficiency is important because interacting with a complex urban simulation or potentially real-world data can be computationally expensive or time-consuming. PPO is generally considered more sample efficient than older policy gradient methods, meaning it can learn a good policy with fewer interactions, saving time and resources.
You mentioned ease of implementation.
Yeah, relatively speaking. Compared to some other advanced DRL algorithms, PPO's core idea is fairly elegant, and there are excellent well-maintained libraries like Stable Baselines 3 that provide reliable implementations. This lets researchers focus more on the problem itself, the environment modeling, reward design, rather than debugging the core algorithm.
Okay, let's get into the core mechanics again. PPO optimizes a stochastic policy. What does that mean exactly?
It means the policy doesn't just output a single best action for a given state. Instead, it outputs a probability distribution over all possible actions. So, for a given city-state, it might say there's a 70% chance placing a booth here is best, 20% chance over there, 10% elsewhere.
And the agent then samples an action based on those probabilities.
Exactly. This inherent randomness allows for exploration, and the goal of PPO is to gradually shift those probabilities towards the actions that lead to higher long-term rewards.
And that clipped surrogate objective, how does it actually guide that shift in probability safely? Let's try to unpack LCLIP a bit more.
Okay, so the core idea is to compare the probability of taking a certain action under the new updated policy versus the old policy.
Yeah.
This gives you a ratio. If the new policy makes an action much more likely, ratio 1, or much less likely, ratio 1, it means the policy is changing significantly.
Right.
PPO's objective function includes this ratio, but it clips it. If the ratio tries to go above 1 plus epsilon or below 1 epsilon, where epsilon is a small hyperparameter like 0.1 or 0.2, the function just uses 1 plus epsilon or 1 epsilon instead.
So it puts a ceiling and a floor on how much that ratio can influence the update.
Precisely. It ignores excessively large proposed changes, whether positive or negative. This prevents the policy from taking massive leaps in a single update, forcing it to make more conservative, incremental improvements within a trust region around the old policy. That's the key to its stability.
That makes sense. It allows improvement, but prevents catastrophic jumps. How does the agent actually gather the data to learn from?
The agent interacts with that simulated city environment we talked about. In each step, it observes the current state, the multi-channel grid, chooses an action, where to place a booth, based on its current policy, and the environment responds with the next state and a reward signal based on that complex reward function.
And it stores these interactions.
Yes, these state, action, reward, next state tuples, these experiences, are collected, often over many steps or episodes. PPO then uses batches of these experiences to calculate the policy update, aiming to maximize the cumulative reward it expects to get over the long run. Libraries like Stable Baselines 3 handle much of this agent environment loop and the optimization process efficiently.
Okay, let's talk about the brain of the agent, the neural network architecture. They used a convolutional neural network, a CNN. Why CNNs for this kind of spatial grid data?
CNNs are really the standard, powerful tool for processing grid-like data, like images, or in this case, our multi-channel representation of the city. Their strength lies in automatically detecting spatial hierarchies of features.
What do you mean by spatial hierarchies?
Well, convolutional filters can learn to recognize local patterns in the input grid, maybe a small area of high AQI next to a traffic source. Subsequent layers can then combine these simple patterns to recognize larger, more complex spatial configurations, like an entire polluted corridor along a highway flanked by dense housing.
So they're good at understanding spatial relationships in the data. What did the input layer look like?
The input layer takes that 50 by 50 by 6 grid we discussed, a 50 by 50 spatial layout, with 6 channels representing AQI, population, traffic, industrial, green space, and the existing booth locations. It's like feeding the network 6 different maps overlaid on top of each other.
And then this data goes through the convolutional layers.
Yes, typically several convolutional layers. The paper might specify something like layers with 32, then 64, then maybe 128 filters. Each filter acts like a specialized pattern detector sliding across the input grid. They usually use small kernel sizes, like 3 by 3, to focus on local patterns and ReLU activation functions to introduce nonlinearity.
What's the purpose of these layers?
Yeah.
Extracting features.
Exactly. They transform the raw input grid into progressively more abstract and informative feature maps, highlighting the important spatial patterns relevant to booth placement.
After the convolutional layers, what comes next? Pooling.
Often, yes, a max pooling layer might be used. Its job is to reduce the spatial dimensions of the feature maps, for example, reducing a 50 by 50 map to 25 by 25. This makes the network more computationally efficient and also helps make the learned features more robust to the small shifts or distortions in the input.
Okay, so condense the information.
Then comes a flatten layer. This simply takes the final 2D feature maps and reshapes them into a single, long 1D vector. It's preparing the spatial information to be processed by standard, fully connected layers.
And what do those fully connected layers do?
The fully connected layer, or layers, takes this flattened vector of features and integrates them. It learns higher-level combinations and relationships between the features extracted by the CNN part. You might have a layer with, say, 256 neurons, again typically with ReLU activation.
And from this integrated representation, how does it actually decide where to place the booth and how good the current situation is.
Right. The network usually splits into two heads at the end. One is the policy head. This outputs the final action probabilities. For a 50 by 50 grid, it might output 2,500 values passed through a softmax function, representing the probability distribution over all possible grid cells for placing the next booth.
That's the actor part, deciding the action. What's the other head?
The other is the value head. This outputs a single scalar value, usually with a linear activation. This value represents the network's estimate of the expected future cumulative reward from the current state, essentially. How good the current city situation looks from the agent's perspective. This is the critic part.
And this value estimate is crucial for guiding the learning, right?
Absolutely. It's used in calculating the advantage how much better an action was than expected, which is key for training the policy head effectively using PPO.
Okay, so it's quite a sophisticated architecture, using CNNs for spatial understanding and then splitting into policy and value outputs. Let's talk training specifics. What are the key steps in the actual PPO training loop?
It follows that actor-critic structure we mentioned. The process generally looks like this. First, you initialize the environment, setting up that multi-channel grid representing Delhi at the start of an episode.
Okay.
Then, the agent observes the current state and performs action selection. The policy network, the actor, outputs the action probabilities, and an action, a booth location, is sampled from this distribution.
Incorporating that exploration element.
Right. Next is the environment transition. The chosen action is executed in the simulated environment. The environment updates, maybe AQI changes, the booth grid is marked and returns the next state, the reward earned for that step, and whether the episode has ended once there were max booths placed.
And store that interaction.
Yes, these state, action, reward, next state, done transitions are stored in a replay buffer or collected over a batch of steps.
Then comes the learning part. How are the advantages calculated?
This is where the critic helps. They often use generalized advantage estimation, GAE. It's a clever technique that looks multiple steps into the future, using the value function estimates from the critic, to get a more accurate and stable estimate of how much better taking a specific action was compared to the average action in that state.
A better estimate of the goodness of an action?
Exactly. Then, using these advantages, the policy update happens. The parameters of the policy network are adjusted using the PPO-clipped surrogate objective function we discussed, usually via gradient ascent, to make actions with positive advantages more likely and those with negative advantages less likely.
With the clipping ensuring stability.
Correct. Simultaneously or alternatingly, you have the value function update. The value network, the critic, is trained to better predict the actual cumulative rewards observed during the interaction. This is typically done by minimizing the mean squared error, MSE, between its predictions and the calculated target values, often derived from the observed rewards and future value estimates.
And what about maintaining exploration?
That's where entropy regularization comes in. An entropy bonus term is often added to the PPO objective function during the policy update. Maximizing entropy encourages the policy to maintain a degree of randomness, preventing it from collapsing too quickly to a deterministic policy and getting stuck in a suboptimal solution.
So it keeps exploring possibilities.
Yes. And this whole cycle, interact, store, estimate advantages, update policy, update value, repeats iteratively over many episodes or batches, allowing the agent to gradually learn and improve its booth placement strategy.
It's a complex dance between acting, evaluating, and updating. The paper likely listed specific hyperparameters used for training. Could you give some examples and explain why certain choices might be made, like learning rate or discount factor?
Sure. Hyperparameters are critical. For instance, learning rate. There's out 2.5e4. This controls how big the update steps are. Too high, it might overshoot and become unstable. Too low, learning can be very slow. It's often tuned carefully. Discount factor, gamma, RIGI, 0.97. This determines how much future rewards are valued compared to immediate rewards. A value close to 1, like 0.97, means the agent is quite farsighted, caring a lot about long-term AQI improvement, which makes sense for this problem. A value closer to 0 would make it myopic, only caring about the next step's reward.
Right, we want sustained improvement.
Policy clip, epsilon. For example, 0.15. This is the PPO clipping parameter we discussed. 0.15 or 0.2 are common values, limiting how much the policy can change per update to ensure stability.
The guardrails.
Entropy coefficient, for example, point 1. This controls the strength of that entropy bonus, encouraging exploration. A higher value encourages more randomness, lower value lets it converge faster, potentially prematurely. It might even be decreased over training.
Balancing exploration and exploitation.
Batch size for Teacher 64. How many experiences are used in each update step? Larger batches give more stable gradient estimates but require more memory and might slow down learning per update.
Trade-offs everywhere.
Total episodes time steps, CG 100 episodes. How long the agent is trained for. Needs to be long enough for convergence, but not excessively long. Choosing these values often involves some experimentation, guided by common practices and the specific problem's characteristics.
So pulling it all together, how did the PPO agent perform during this training process based on the paper's findings? Did it successfully learn?
Yes, the overall performance reported was very positive. The agent effectively learned an optimized policy for booth placement.
How did they tell?
They looked at several indicators. The training reward curves generally showed an upward trend, indicating the agent was getting better at maximizing its reward signal. Metrics tracking AQI improvement likely showed significant reductions compared to the initial state.
And the internal mechanics.
The training loss curves for both the policy and value functions typically stabilized, indicating the learning process was converging rather than diverging wildly. The policy entropy likely decreased over time, showing the agent moving from random exploration towards a more deterministic, confident strategy. These signs collectively pointed towards successful learning and convergence to an effective policy.
Excellent. So the training process worked. Now for the exciting part. Proving the advantage. Let's get into the results and the comparative analysis against the baseline strategies.
Right, so they compared their PPO agent against two simpler methods.
The first being random placement.
Yes, random placement. Here, booths were placed essentially randomly across the grid, although they likely still respected basic constraints like minimum distance.
What's the point of that?
It serves as a basic baseline. What happens if you have no strategy at all? You'd expect broad spatial coverage just by chance, but very little targeted effectiveness. The AQI reduction would be suboptimal, happening purely incidentally.
Okay, the no strategy baseline. What was the second one?
The second was greedy high AQI placement. This is a more intuitive heuristic.
How does it work?
It simply places booths sequentially in the available grid cells that currently have the highest AQI value, while still respecting constraints like minimum distance and maybe avoiding green spaces.
So always attack the worst spot right now.
Exactly. It's greedy because it only looks at the immediate best option without considering the longer-term or broader spatial consequences.
What would you expect from this strategy?
You'd expect it to achieve significant AQI reduction, especially locally in the targeted hotspots. It might even outperform PPO on that single metric initially. However, you'd also expect it to potentially neglect areas with slightly lower AQI but high population, lead to clustering of booths, and lack overall spatial balance and long-term optimization.
Right, potentially inefficient overall. And the third strategy is the PPO-based placement itself.
Yes, the intelligent learn strategy. Here, the placement decisions are made by the trained PPO agent, which considers all those factors: AQI, population, traffic, constraints based on its learned policy.
And the expected outcome here.
The expectation is a balanced, adaptive placement. It should target high AQI areas, but also prioritize high-impact zones, population, traffic, avoid constraint violations, and achieve a more strategically distributed coverage for maximum overall benefit, not just maximum immediate AQI reduction.
The paper likely included visualizations of these placements. Can you describe what those figures might have shown for random, greedy, and PPO?
Typically, yes. For random, you'd see booths scattered almost haphazardly across the city map. Some in useful spots, many likely not. A very diffuse pattern.
Okay.
For greedy, you'd likely see distinct clusters of booths concentrated heavily in the areas identified as having the highest initial AQI. Large parts of the city might have no booths at all.
Very focused, maybe too focused.
Right. For PPO, the visualization would likely show a more strategic distribution. Booths might still appear in high AQI zones, but also potentially near major traffic corridors or dense residential areas that the greedy method might have missed. It would look less clustered than greedy, more targeted than random and intelligent compromise.
These visual patterns really help understand the different underlying strategies.
Absolutely. They give you an immediate qualitative sense of how each method approaches the problem.
Beyond the final placement maps, the paper probably showed plots of the PPO agent's training performance over time, like Episode rewards. What did that typically show?
The episode rewards plot usually shows the total reward accumulated by the agent in each training episode. You'd expect to see fluctuations, especially early on, due to the inherent randomness, stochasticity of the environment and the agent's exploration.
But the trend should be.
The overall trend should be upwards. As the agent learns, it should get better at maximizing its reward signal. So despite the noise, you look for a clear increasing pattern over the episodes, indicating effective policy learning.
Okay. What about a plot of AQI improvement percentage over training?
That plot would track how much the average AQI across the city improved as training progressed. Typically, you'd see rapid improvement early on as the agent learns the basics. Then it might start to plateau.
Plateau. Is that bad?
Not necessarily. A plateau often indicates that the agent is converging to a stable, robust strategy. It's found a policy that achieves significant improvement and further training yields diminishing returns because it's already close to the optimal solution it can find within the given constraints and objectives. It shows learning has saturated effectively.
Got it. Another key visual might be the distribution of AQI values across the grid cells before and after PPO. What's the significance of that?
Ah, yes. The AQI distribution plot, often a histogram, is a really powerful aha moment visual. You plot the number of grid cells, y-axis, against different AQI level bins, x-axis.
So it shows how many areas have low, medium, high pollution.
Exactly. You typically show two distributions overlaid, the initial one before intervention and the final one after the PPO agent placed booths. The before curve might be shifted towards higher AQI values. The after curve, say in orange, should be clearly shifted to the left towards lower AQI values.
Meaning fewer cells with high pollution, more cells with low pollution.
Precisely. It visually confirms that the PPO strategy didn't just lower the average AQI, but actually shifted the entire distribution, improving air quality across a significant portion of the urban grid.
That's a strong indicator. What about the internal learning metrics like training losses?
Looking at the training losses provides insight into the stability of the learning process. You typically see two loss curves.
This reflects how much the policy is changing. Thanks to PPO's clipping, you'd hope to see this loss decreasing but remaining relatively stable without huge spikes.
This reflects how well the critic network is predicting future rewards. This often fluctuates more, especially in complex environments, as the agent explores and the value estimates get refined. But ideally, it should also show a generally decreasing or stabilizing trend.
So stable policy loss, maybe more wiggly value loss, but both generally improving.
That's a good sign, yes.
And the last one, often shown as policy entropy. What does that tell us?
Policy entropy measures the randomness or uncertainty in the agent's policy. Initially, when the agent is exploring randomly, entropy will be high. As it learns and becomes more confident about the best actions, the policy becomes more deterministic, and entropy should decrease sharply.
So a steep drop in entropy is good.
Generally, yes, it indicates convergence. However, you might see it level off at a small positive value or have minor fluctuations later on. This can actually be healthy, indicating the agent retains a small amount of exploration, due to the entropy bonus, to potentially adapt if the environment changes or fine-tune its strategy. A complete collapse to zero entropy might mean it stopped exploring too soon.
Okay, so putting all those training plots together, rewards, AQI improvement, distribution shift, losses, entropy, what's the big picture interpretation?
The big picture is confirmation of successful learning. The rising rewards and AQI improvement show the agent is achieving its goal. The AQI distribution shift proves the real-world impact across the city. The stable losses confirm the learning process itself was sound and robust thanks to PPO. And the decreasing entropy shows the agent converged from exploration to an effective, learned policy. Collectively, they build a strong case that the DRL approach worked as intended.
Excellent. Now for the quantitative showdown. The paper likely had a table comparing the final performance of PPO, greedy, and random across multiple key performance indicators, KPIs.
Yes, that's where you get the hard numbers.
Let's go through the key metrics. Overall, AQI improvement percent.
Here, as we predicted, the greedy strategy might actually score slightly higher or very close to PPO. For example, maybe greedy got 25.8% overall AQI reduction and PPO got 25.4%.
So greedy wins on pure AQI reduction.
Potentially, yes, on that single metric, but that's only part of the story.
Right. What about coverage improvement percent?
Random placement would likely score highest here, simply because it spreads booths everywhere by chance. PPO would likely have better coverage than greedy, which tends to cluster.
Okay. Now the crucial ones. Population impact score and traffic impact score. How did PPO fare there?
This is where PPO really shines. The results would likely show PPO significantly outperforming greedy on both population impact and traffic impact. For instance, PPO might have a population impact score twice as high as greedy's.
Why the big difference?
Because PPO's learned policy explicitly incorporated population and traffic density into its decision-making via the reward function. Greedy ignored those factors, only focusing on the raw AQI number. Random, of course, would have very low scores here, as its placements weren't targeted at all.
So PPO delivered cleaner air where it most affected people and traffic pollution sources.
Exactly. It optimized for human exposure and key emission areas, not just abstract AQI values.
What about industrial impact score?
PPO would likely score well here too, again, because industrial influence was part of its input and potentially reward. Greedy might score lower if the highest AQI spots didn't happen to coincide with industrial zones.
And green space violations. Did any strategy place booths where it shouldn't have?
PPO, having been trained with constraints, should ideally have 0 violations. Random might accidentally place some in wean spaces if not constrained. Interestingly, the greedy method, in its single-minded pursuit of the highest AQI, might actually violate the green space constraint if a park happens to be in the most polluted cell. The paper might report greedy having 1 violation while PPO has 0.
Highlighting PPO's ability to respect constraints.
Yes. And finally, spatial entropy. What does that measure? Spatial entropy provides a quantitative measure of how evenly the booths are distributed across the space. Higher entropy means a more even, less clustered distribution.
How would the strategies compare here?
Random would likely have high spatial entropy, very spread out. Greedy would have low spatial entropy, highly clustered. PPO would likely fall somewhere in between, achieving a balance between targeting key areas and maintaining reasonable spatial coverage. It reflects that strategic balanced distribution we saw visually.
Okay, so PPO wins significantly on impact scores and constraint adherence, while greedy might slightly edge it on raw AQI, and random wins on pure spread.
That's a good summary. It shows why looking at multiple metrics is crucial.
And the radar plot visualization brings this all together, right? How does that work?
The radar plot, or spider chart, is perfect for visualizing this multidimensional performance. Each axis radiating from the center represents one of the key metrics: AQI improvement, population impact, traffic impact, industrial impact, maybe coverage, etc., normalized usually to a scale of 0 to 1.
And each strategy gets a shape on the plot.
Exactly. You plot each strategy's normalized score on each axis and connect the dots, forming a polygon. The larger the area covered by the polygon, the better the overall performance across all dimensions.
What would the shapes look like for PPO, greedy, and random?
PPO's shape would likely be the largest and most well-rounded, covering a significant area on nearly all axes, visually demonstrating its superior balance and high performance across AQI, population, traffic, and industrial impact.
The dominant shape.
Greedy's shape would likely be skewed. It would stretch far out on the AQI improvement axis, but be significantly smaller on the population, traffic, and possibly industrial impact axis, showing its narrow focus.
A spiky shape.
Right. And random shape would probably be relatively small overall, particularly on the high-impact dimensions like population and traffic, maybe extending a bit on coverage, reflecting its general inefficiency.
So the radar plot makes it visually obvious that PPO provides the most effective and balanced solution overall.
Absolutely. It powerfully underscores why PPO is superior when you consider the multiple, often competing objectives involved in real-world urban air quality management. It's not just about one number, it's about the holistic outcome.
Fantastic. So let's step back and discuss the key insights from this study. What are the main takeaways about PPO's robustness and the limitations of the simpler methods?
I think the study really drives home PPO's robustness for this kind of complex optimization. It showed it can effectively juggle those competing goals, reducing overall AQI, yes, but also prioritizing human exposure near populations and traffic, ensuring efficient spatial distribution, avoiding clustering. It leads to an adaptive, balanced deployment strategy.
And the traditional methods.
Their limitations become starkly clear. The greedy heuristic, while maybe getting good immediate AQI results, fundamentally lacks that long-term optimization perspective and spatial balance. It can be inefficient, redundant, and miss key impact areas. And random, well, it's just strategically ineffective.
It also highlighted the importance of accounting for the city's complexity, right?
Definitely. The importance of spatial heterogeneity. The DRL approach fed with that multi-channel data, could actually account for the complex urban environment, smartly avoiding places like green spaces while actively targeting those high-impact zones. That's a major advantage.
And the training itself.
The analysis of the training metrics really confirmed the stability and convergence of PPO. We saw how it effectively learned, converged robustly, and transitioned from that initial broad exploration to a more focused, reliable, and deterministic policy. It validates the whole learning process.
What are the broader implications of this kind of work beyond just placing air purifiers?
I think the major implication is the power and importance of multi-objective optimization in complex urban planning scenarios. This research provides a strong case study. It shows we need to move beyond single metric goals.
It's not just about lowering pollution.
Right, it's about doing it in a way that maximizes overall community benefit, considering where people live, where they work, how they travel, the impact of industry. This AI-driven framework offers a potential blueprint for how cities can leverage data and ML to make smarter, more sustainable decisions across many domains, not just air quality.
That's a really exciting prospect. But of course, no model is perfect. The researchers themselves acknowledged limitations and pointed to future work.
Yeah.
What were some of the key model simplifications they mentioned?
One significant one is the Gaussian influence model they use for both feature influence and Booth effect. It's a simplification. Real-world pollutant dispersion is much more complex.
Where does the Gaussian model miss?
It doesn't explicitly account for intricate dynamics like chemical reactions between pollutants in the air, or how local topography, hills, valleys, tall buildings can drastically alter airflow and dispersion pattern.
Or weather?
Exactly. Which leads to the second big limitation, the general lack of meteorological considerations. The model, as described, largely assumes static conditions, particularly regarding wind speed and direction.
But wind is obviously crucial for moving pollution around.
Hugely crucial. Ignoring dynamic wind patterns means the assumption of a relatively static AQI grid isn't fully realistic. Air quality can change rapidly based on meteorological shifts.
So how could future work address these simplifications?
For dispersion, future work could involve integrating more sophisticated models, perhaps physics-based computational fluid dynamics, CFD simulations, though those are computationally very heavy. Or maybe data-driven spatiotemporal pollution forecasting models that learn complex dynamics directly from sensor data.
And for the weather dynamics?
They suggest exploring dynamic placement adjustments, maybe using frameworks like Markov decision processes, MDPs, where meteorological conditions are part of the state, allowing the AI to adapt its strategy based on current wind or rain, or perhaps using physics-informed neural networks that try to incorporate physical laws into the learning process.
Okay, so making the environmental simulation itself more dynamic and realistic. What about practical real-world constraints beyond the physics?
That's another key area, policy and deployment constraints. The current model optimizes placement based primarily on environmental factors and simple constraints like distance. It doesn't fully grapple with the messy realities of real-world deployment,
Such as
specific city regulations, land use policies that might forbid building on a technically optimal spot, public infrastructure limitations like access to power for the booths, or simply the economic feasibility, the cost of acquiring land, installing the booth, maintaining it.
the AI might find the perfect spot on the map, but you literally can't put a booth there because it's private property or costs too much.
Exactly. The model doesn't currently incorporate that layer of socioeconomic and political reality.
How could that be addressed in the future?
Future work could involve integrating economic and policy-aware optimization frameworks. This might mean adding cost estimates or policy compliance checks directly into the reward function or constraints. Maybe exploring game-theoretic approaches to model interactions between different stakeholders, city planners, residents, industry.
Making the AI not just environmentally optimal, but also practically and politically feasible.
That's the goal, yeah. It's a much harder problem, but essential for real deployment.
And the final limitation often mentioned is scalability. Delhi is one city. What about applying this to much larger regions or even national networks?
Scalability is definitely a challenge. The computational complexity grows rapidly with the size of the grid, the state space, and the number of potential actions. Applying this exact approach directly to, say, all major cities in a large country might be computationally intractable.
So how do you scale it up?
Researchers are exploring techniques like hierarchical reinforcement learning. You might have a high-level agent deciding which region of a city needs attention, and lower-level agents optimizing placement within those regions. Or multi-agent reinforcement learning, MARL, where multiple agents coordinate to cover different parts of the city or different aspects of the problem. These are active research areas aimed at tackling large-scale applications.
Fascinating. So lots of avenues for future research to make these powerful tools even more realistic and applicable.
Absolutely. This study provides a fantastic foundation, but there's always more complexity to capture.
What an incredible deep dive this has been. Just to recap for everyone listening, we've explored how a deep reinforcement learning framework, specifically using Proximal Policy Optimization, or PPO, offers this really adaptive, efficient, and robust solution for strategically placing air purification booths.
And we saw clear evidence of how it outperforms those traditional, simpler heuristic methods like random or greedy placement, especially when you consider multiple objectives.
It really highlights the transformative role that this kind of data-driven decision-making can play in creating more sustainable, healthier urban environments.
It really does. Leveraging AI like this allows us to move towards interventions that are not just technically effective, but also holistically beneficial, considering the complex fabric of the city.
And thinking bigger picture, this is just the beginning, isn't it? This kind of AI-driven spatial optimization. You can imagine it being applied to so many other complex urban challenges.
Oh, definitely. Optimizing public transit rates in real time based on demand and traffic, figuring out the best deployment strategy for emergency services during a crisis, even managing local energy grids more efficiently. The potential is huge.
But it also raises a provocative thought, perhaps. Even with the most sophisticated AI, like this PPO system learning complex strategies, how does it truly grapple with the elements of a real city that are inherently unpredictable or perhaps even unquantifiable by our current sensors and models? The sheer moment-to-moment variability, the human element that doesn't fit neatly into a grid cell, what are the ultimate limits here?
That's a profound question, and it's the crucial interface between the AI model and the real world. While AI offers immense power for optimizing based on the data it has, deploying it effectively always requires acknowledging those inherent limits, the unpredictable dynamics, the data gaps, the model simplifications. Integrating these systems requires ongoing validation, adaptation, and frankly, human oversight that understands the context beyond the algorithm.
A critical point. AI is a powerful tool, but not a magic wand. Well, we hope this deep dive gave all of you listening a fresh perspective on the power of AI to tackle major global issues like air pollution, and perhaps equipped you to think more critically about the smart cities we're building for the future. Remember, to stay updated on the latest AI and ML research papers like the one discussed today, you can visit our webpage. The link is in the bio.
Thanks for tuning in.
Thank you for joining us on the deep dive. We'll be back soon with another exploration into the fascinating world of AI.